Following on from the previous episode, we asked the question, has the many orders of magnitude problem always existed? In other words, has the electrostatic force always been 42 orders of magnitude greater than the gravitational force throughout cosmological history? If the answer is no, why would we think so? Well, the answer to the second question, of why we might think that the many orders of magnitude problem may have varied over cosmological time, is surprisingly simple to resolve. Consider this. In episode 1, we showed utilizing Buckingham pi theory, that gravitational acceleration and the electrostatic charge are not related. From the perspective of general relativity, this means that electrostatic charge does not curve spacetime. The mass associated with electrostatic charge curves spacetime, but the electrostatic charge itself does not curve spacetime. Hence, if we accept general relativity as being the source of truth, this means that as spacetime has expanded over cosmological time, space-time curvature has also changed, relative to its initial state at the instant of the Big Bang. In fact, we have demonstrated in our publication titled, The History of the Cosmos, that the cosmological curvature parameter has evolved over cosmological time. Please refer to Table 14 in the stated publication for more information. Therefore, if the cosmological curvature parameter has changed over cosmological time, and the electrostatic charge is not related to space-time curvature, then the electrostatic force to gravitational force ratio, that is, the many orders of magnitude problem, must have varied throughout cosmological history. At this juncture, it is essential for viewers to understand that constant cosmological curvature, throughout cosmological history, is an unfounded position. No physical evidence exists to confirm the doctrinal instance of never-changing, permanently constant, cosmological space-time curvature. Let's cast our minds back to episode 8. That was the episode containing our periodic table of harmonic solutions, in which we showed that it was possible to utilize Buckingham pi theory to describe all fundamental particles as a harmonic multiple of a reference particle. Please refer to episode 8 for more information if required. Thus, by applying Buckingham pi theory once again as a scaling technique, we may describe the cosmological growth of the electrostatic to gravitational force ratio over cosmological time. That is, from the instant of the Big Bang, such that the Hubble radius is denoted by r sub s, to the present day, where the Hubble radius is denoted by r sub phi. By following the process arrows as indicated, pausing and rewinding as required, we arrive at the force ratio as a function of cosmological radius, denoted by small r, in the bottom right-hand corner of the screen. By substituting appropriately, we arrive at an expression for electrostatic to gravitational force ratio, which should be easily understood by most viewers. When we plot the force ratio equation in the time domain, we see that the electrostatic force equaled the gravitational force very soon after the Big Bang. Specifically, it occurred during the cosmological inflation process. When the force ratio equaled unity, the many orders of magnitude problem did not exist. Hence, the many orders of magnitude problem started at T4. When we turn our attention to the cosmic microwave background radiation, we see that the temperature of the universe at the instant when the force ratio equaled unity was approximately 10 to the power of 31 Kelvin. At the bottom of the screen, we have calculated the value of the force ratio at various cosmological epochs. You can see that the many orders of magnitude problem, that is, the force ratio, has been increasing since the Big Bang. The results presented in red show the details of the force ratio change at various cosmological epochs, whilst the information appearing in purple at the bottom right-hand corner of the screen shows the change in force ratio relative to the present epoch. From this, we see that when the universe was 3.6 billion years old, the force ratio was 64% lower than today. Conversely, we see that the electrostatic to gravitational force ratio will be 67% higher, 14.57 billion years from today. Please pause the video and analyze the information presented. En route to our cosmological history solution appearing on the previous slide, we pass through an important step, identified by the let command. With this command, we assign the solution of the form shown, that is, the force ratio is raised to the power of 1/2. But why did we assign this value? Why not some other power? Well, let's have a look. In the first candidate solution, we look at the most obvious condition to evaluate. By following the process arrows, we see that the power term, AA, yields a value very close to our applied solution. Thus, the origin of our applied solution is the rounded value of the first candidate solution. However, the next obvious question is, why did we settle for the first candidate solution? We can answer this question by reformulating the electrostatic to gravitational force ratio, in more generalized terms, based upon slide 2. When evaluated as appears on screen, we can see that only one result generates the many orders of magnitude problem correctly. Thus, we have confirmed that our initial premise, appearing at the top of the screen, was a wise choice. The final step in the formulation of any solution involves testing its predictions. Appearing on screen are our predictions for the electrostatic to gravitational force ratio for the next billion years. Now is a convenient time to ask some important questions. Firstly, why does the standard model of cosmology expect the force ratio to remain constant forever? Well, the short answer to this is that it's an assumption, without any evidence to support it. In other words, it is blindly accepted as doctrine. So then, the reciprocal question should be asked, that is, why do we expect to see a change in the electrostatic to gravitational force ratio over time? The answer to this specific question has three parts. Firstly, at a moment prior to the Big Bang, the force ratio was undefined, however today, it is defined. Its transition from an undefined state to a defined state could not have been instantaneous, it must have taken some time. Secondly, we showed in episode 34, that the origin of the many orders of magnitude problem is rooted in the quantum vacuum. Hence, as the quantum vacuum changes via accelerated cosmological expansion, the force ratio must also change. And thirdly, we showed in episode 1, that no relationship exists between electric charge and gravitational acceleration. Hence, in accordance with the electrogravimagnetic construct, all matter evaporates over time. Thus, we expect that the force ratio must also change. The last and most important question to ask is, can we test our predictions? The short answer is yes, we can, by direct physical measurement. Given the rapid progress of technology, we would be hopeful that it is possible within the next 100 years, probable within the next 1,000 years, and certain within the next 100,000 years. However, taking a step back and looking at a bigger picture, we predict that the change in the force ratio over the next 1 billion years is just 5%. On face value, this appears to be a plausible prediction. Let's now summarize what we've learned so far. The key takeaways from this episode are, number 1, if the cosmological curvature parameter has changed over cosmological time, and the electrostatic charge is not related to space-time curvature, then the electrostatic force to gravitational force ratio, that is, the many orders of magnitude problem, must have varied throughout cosmological history. Number 2, a moment prior to the Big Bang, the force ratio was undefined, however today, it is defined. Its transition from an undefined state to a defined state could not have been instantaneous, it must have taken some time. Number 3, we showed in episode 34, that the origin of the many orders of magnitude problem is rooted in the quantum vacuum. Hence, as the quantum vacuum changes via accelerated cosmological expansion, the force ratio must also change. Number 4, given the rapid progress of technology, we would be hopeful that it is possible to measure a change in the force ratio within the next 100 years. And number 5, we predict that the change in the force ratio over the next 1 billion years is just 5%. On face value, this appears to be a plausible prediction. For viewers wishing to consult publications relevant to this episode, you may do so by accessing the links shown.